Hello class. In this video we're going to apply what we've learned about inscribed and central angles in order to solve geometry problems. So to start off, in this problem we want to figure out what the measure of angle DEA is. And our problem involves both x and y, so we're going to want to write a system of equations and solve it for y. And there's a lot going on here, so I think this will be easiest if we break it down and go step by step and justify each step with a reason. So we're using the letter y to represent the degree measure of angle DEA. And what would the measure of angle DBA be? Well, DBA is an inscribed angle that intercepts arc AD. But so is angle DEA. So since they're both inscribed and they intercept the same arc, they have to have the same measure. So this is also y degrees. What about angle ADB? What's special about that angle? Well, triangle ADB is a triangle that's inscribed in the circle, and one of the sides is a diameter. And so this is Thales' theorem. We know we have to have a right triangle. Another way to think of it, instead of Thales' theorem, is you could say, well, we have an inscribed angle that intercepts an arc that measures 180 degrees with a semicircle, and 180 divided by 2 is 90. And why can we write this? 46 plus x plus y plus our 90 degrees. Why do we want to add those together? What's that equal? Well, that equals 180 because those are the angle measurements in this triangle, the triangle ABD. And so if we do some algebra here, x plus y equals 44. So that's one equation. Now we want to write another equation with y, which they claim is y equals x plus 32. So why is that? Well, if we look at triangle ACE, which I'm highlighting in red here, where does that come from? Well, we have a y degrees as an exterior angle, and the two remote interior angles are x and 32. So we know that that's a property of triangles and exterior angles that we have. So we just add the two remote interior angles, and that gives us the exterior angle measure. And now we want to combine these, so we're going to substitute. So instead of y, we plug in x plus 32. So we're missing a 44 here. And now we do some algebra. 2x equals 12 divided by 2, and we get x equals 6. Plug in the 6 up here for x, and we can figure out what y is. Y is 38. So our missing angle is 38 degrees. Here we have a theorem that states if we have 4 points where B and B prime are on the same side as line AC, so if we connect A and C with a line, we'll see that they're both on this upper half plane, and angles B and B prime are congruent, then all 4 points are on the same circle. Now, we can prove this by doing an argument by contradiction. So we're going to do a little informal argument down here. So we want to say that B prime is on the circle. But what if it's not on the circle? What if it's outside the circle? So we're assuming that B prime is outside and congruent to B, so they're both x. And if we draw in this segment here, we have an inscribed angle. So this intercepts arc AC, as does angle B, so they have to both be x. So why is this construction over here impossible? Well, we have an exterior angle here. So this x equals this remote interior angle x plus this one over here, which we can call y. So we get the equation x equals x plus y. But if we subtract x from both sides, what happens? We end up with 0 equals y. So we have an angle that measures 0 degrees, which is not the case here. Y is clearly a non-zero angle, right? So that's impossible. And the case where we have B prime inside the circle is also impossible because here we once again have an exterior angle. So x is x plus y, so y is 0 again. So it's impossible for B prime to be outside the circle. It's impossible for it to be inside the circle, so it must be on the circle. Here we have a computational example, which I would like you to try on your own, and then come back here and check your work with mine. So try this now, and use the hint, use Thales' theorem. So if you followed the hint for angle BEC, you saw that angle the angle BEC is 90 degrees. Right? This has to be a right triangle because BC is a diameter. And this triangle here is isosceles because it has congruent legs. And we know that in an isosceles right triangle, that those two angles have to be 45. Right? So they have to be the same, and 45 plus 90 gives us 180. And how does that help us? Well, Angle EDC, which has measure x degrees, intercepts arc EC. And we know it's going to be the same as any inscribed angle that intercepts the same arc. But we know that our 45-degree angle over here intercepts that arc and it's inscribed. So we know that x must also be 45. Okay, same idea. Try this example on your own, and then come back here and check your work with mine. So they give us a central angle here, and we have two inscribed angles that intercept the same arc, BC. So we know that the inscribed angles have half of the measure of that central angle. So this is 52, and this one's 52. Now we want to know what x degrees is, and we see that we have vertical angles here. So if we could figure out what angle EGF is, that's going to be the same as x. So let's see, we have a quadrilateral here, and this is 30 degrees. So if we could figure out what these two angles are in this quadrilateral, we can combine that with the 30 degrees to figure out what angle EGF is. Well, these are supplements, so we know that that must be 128 because 180 minus 52 is 128. And the same deal with angle GFD. And what do the interior angles in a quadrilateral add up to? They add up to 360 because we could always decompose it into two triangles. So 2 times 180 gives us 360. So our missing angle right here, EGF, is 74 degrees. So we just take 360, subtract 128, 128, and 30, and we get 74. And so that must mean that x is 74 because we have vertical angles. In this video, we learned how to apply what we know about inscribed and central angles to solve geometry problems. Thank you for watching this video.